All right. So yeah, it looks like I'm recording. So um anyways, I never thought about this before, but all my videos recently have been on the book but how do it know? Um so that's where all my information is coming from in the recent videos. And I never like when I thought about how a computer does multiplication, my naive brain was like, oh, it just adds several times over and over again. Well, um, you don't really need to do that. This is two's complement. This is subtraction. That's different. I can do a video about that later. Um, I actually already knew about two. I think that's two's complement. I already knew about two's complement. Um, I think that's what that's called. But anyways, I never thought about this. All it does is, so this is the bottom number. So I guess I can get GIMP out. New. Why not? I need an actual tablet eventually. I have an X220, X200 ThinkPad, but I don't know. It's just hard to record videos with that because it's just old. If I have two binary numbers, well, I guess this shows it pretty well. You see, if you have two binary numbers right here, if the if the bottom you start from left to right, right, and from the bottom number, and this bottom number right here is one. So what do? We copy the whole top number over. That's what we did. And this next bottom number is not one. So if it's one, we copy the whole top number. If it's not one, we don't. And then we also shift to the left one. So in this case, this bottom number is one, and the top number is one. So boom. Let's see if I'm doing this right. If the digit of the bottom number is a 1, you put the top number in the answer. Yeah, okay. So yeah, this one's a 1, then you take the top number, put it as the answer. And this one was a 0, so you just put 0. Okay, this one's a 1, then you take the top number and put it as the answer. And every time we put down the answer, we gotta shift to the left one. And then we keep doing that. The rest of these are all zeros, so we just have a bunch of zeros ending here. And then we just, go all the way down and just add all these together. And what we get, I just realized this doesn't even line up. I never caught that before. Oh, 1 and 1. That'd be 0, 1. Okay, so that's shifting this to the left. That makes sense. Okay. And then this is 1. Okay, yeah. So that gets us our answer, right? But we're also we're adding all of these together too. So we're doing addition, but we're only doing addition 8 times. Yeah. So instead of doing 8 addition, so if your number is 3 times 100, or 100 times 100, instead of doing addition 100 times, you're only doing it 8. So this kind of saves some steps. And I never thought about it. And it shows they in the book they do kind of make your own simple programming language or machine code, not machine code. I'm sorry, assembly language for this computer. So I looked at that and I'm like, wait, I think I could remake that in nasm. And bear with me because I forget a lot of the terms when it comes to nasm, and I'm not claiming to be an expert in assembly by any means. In fact, I'd say that I'm pretty beginner. I've learned basic stuff in assembly, and I've done basic stuff really, really basic, like getting input and output from the terminal and stuff like that. And obviously, uh, but Yeah, I got my function prolog. I push the stack, then I pop the function prolog here. And I think the function prolog is necessary for like certain C things, because when C calls a function, it needs the function prolog, and I think it's called an epilogue. I don't know, something like that. I don't know. I just know you need to pop and push it on the stack, and then so in this case, this is really not really interesting here. So they say they're using R0 contains the top number for the multiplication problem. R1, I'm sorry, R0 contains the bottom number, but I don't think it really matters which one's the top or the bottom. Well, actually, I don't know. I don't think it does, because if I execute this program right now, and it's going to give me 12, but if I switch 4 and 3, because these are two numbers that are multiplying, it should give me the same answer. Yeah, so I don't think it matters which one is the top or the bottom. So R0 contains one number, R that you're multiplying, R1 contains another number you're multiplying, R2 contains the answer, and R3 is used to jump out of the loop after going through it 8 times. And what they do with this R3, you can see they put it says data. So they're just taking R3, like this is what I did here. I've just moved it to R, they're taking this number, moving it to RAX, or R3. So they're putting 1 in R3, and then what they do is they keep shifting it to the left until a carry flag happens. And if a carry flag happens, you know that we just went to the end of the byte. So that's how they determine that this thing has happened 8 times. And then they XOR R2 by itself to just clear out the flag with 0. And what we're doing here is basically, obviously, this process that you see up here. And, we're clearing the carry flag. This says clear flags, but I just did clear the carry flag here, because that's the only flag we need to worry about clearing. So we're clearing the flags. We're shifting, what is it, the bottom number? It doesn't matter which. You just have to, yeah, we're shifting the bottom number. We're going to say R0 is the bottom and R1 the top, even though it conceptually doesn't really matter. We're shifting the bottom number to the right. And then if there's a carry, then we're going to move to here. And we're not going to jump to here. So if there's a carry when we shift to the right, then what we're going to do is we're going to clear the carry flag, and then we're going to add the top number to the total answer. So basically what this is doing, this shift to the right, is basically checking if the binary number to the far right is a 1 or a 0. And if it is a 1, then we're just going to add it to, R2, which right now is 0. And then, if it's not a 1, then we're just going to skip it and go down here. And then we're going to clear the flags again, shift to the left, what is this, the top number? So we're going to also shift to the left the top number, because they need to align with each other. And then we're going to, do our shift counter 1, so this number is going to move to the left 1. And then if there was a carry, meaning this R3 got to the end, then we're just going to exit. If not, we're just going to do this whole thing again. So I did this in nasm, and it's a little different. It's pretty similar to this structure. I actually kind of use this to make this. So we got our format string for printf. So, I got my extern printf here. Then I have my format string, which is just, the number for printf. And then I push on the function prolog. And then I basically I do the same thing in this example, but instead of R0, R1, R2, and R3, I did RAX, RBX, RCX, and RAX, RBX, RCX, and I don't think there's a 4. Yeah, RCX. So R0 is RAX, R1 is RBX, R3 is RCX. That's kind of how I did it. So these are the two numbers I want to multiply together, and I put them in R0 and R1, or RAX and RBX. I move one. Oh yeah, and my brain is. Oh wait. RAX is R0, RBX is R1, RCX is R. Wait, RCX is R2, then RDX is R3. I said that wrong because it's 0. I don't know. Anyways, so then RDX, gets the number 1. This is determining if we're going to carry. Determine if we're done with the operation. Then RCX gets cleared out because that's what has the answer. Clear the carry flag. Shift right RAX to check to see if it has the 1. If it does have a 1, then we're going to jump and make sure that we're adding. If it doesn't, then we're just going to skip the add part and go to the no add part. We're going to clear the flag, shift left, RBX, which is our top number, and then we're going to shift left to see our register to see if we're done, and if it gets to the end, then we just skip, go to the end right here, and if not, we just do it all over again back here in the loop. So yeah, and then right here, calling printf, I have the RDI, the destination, RSI, I think of source, So format, I got the format string, then I have the answer, RCX here, that's going to the source. RAX, I think that has to do with like floating points or something like that, and there's none, so I put 0, and then I just call printf to return the answer. So yeah, and I'm pretty sure like you can do like what is it, MUL or something like that, but this is just a different way of looking at it, I guess. So let's pick 2 different numbers. I think they have to be 16-bit. I'm sorry, 8-bit? I think they have to be 8-bit. Excuse me. So if I did 4, 3, 4, I just did 4 and 3. Let's try to do higher numbers. See if this still works. Seems to still work. It's interesting. 55 and 100, you know what that is. So it still seems to work with, larger numbers. Actually, that makes sense, because in this case, we're only working with what? 8 bits, but RAX is 64-bit, so we're working with 64 bits instead of X, because it's the RAX. It's a quad word or whatever. So yeah, it can work with bigger numbers than this could work with. But yeah, I don't know, that's something simple I learned.